Okay. So, hello everyone. It is a big pleasure to see you all here. So many people who joined us from different parts of the world, and we are very happy. As we announced, today we start a seminar series called Ukraine Seminar for Fundamental Physics. It will highlight the latest development in fundamental physics, spanning from particle physics to cosmology and gravity. So it will connect the smallest and the largest scales in our universe. The main intention of this seminar is to promote scientific interaction with Ukrainian scientists during wartime and to lay down the foundation for future scientific collaborations and exchange visits. We would like to emphasize in the very beginning, and this is the common thought of all organizers, that we strongly condemn the war unleashed by Russia against Ukraine. And we call on all civilized countries and the scientific community in particular to show their solidarity with Ukraine and their support to the Ukrainian people. And this seminar should be like one of the examples of this support. This seminar is organized on the initiative of Professor Niall Turok from University of Edinburgh, United Kingdom, and the Perimeter Institute in Canada, by Professor Mikhail Shaposhnikov from École Polytechnique Fédérale de Lausanne in Switzerland, and by Professor Stanislav Elginski from Taras Shevchenko National University of Kyiv. And since today we have the first seminar, I would like to invite the organizers to say a few opening words. Please, Niall, you're very welcome.
Okay, thanks so much, Sasha, and just a very warm welcome to everybody attending. Thank you for joining and demonstrating your support. I think let me just begin by saying the obvious. Many of us were absolutely horrified by the Russian invasion of Ukraine, and we continue to be horrified daily by the continuing atrocities. The spirit of this seminar is actually to do something, however modest, to demonstrate our support and solidarity with Ukraine and with the Ukrainian people. We hope this seminar obviously will serve to encourage researchers and students working in Ukraine under very difficult conditions, and longer term to build connections and friendships and partnerships and collaborations which we hope will be of value in the future. And, we're all looking forward to helping in whatever way to building something special in Ukraine for the future. I want to thank Sasha and Stanislav in particular for taking this idea forward and their coordinators in Ukraine. Absolutely an honor for me to work with them. And let me just comment very briefly on why I think this is actually very timely in the world of physics and theoretical physics. We're facing a time of unique challenges. Many people would, I think, concede that the dominant paradigms of approaches to, let's say, the next stage of fundamental physics, by and large, have not succeeded. We can mention string theory, supergravity, supersymmetry, and many other attempts. They're all very interesting, and we've learned a lot from them, but we see no sign of those phenomena in nature. On the contrary, nature has turned out to be amazingly simple. At Large Hadron Collider, we see the Higgs boson and nothing else so far. In the larger scale in the universe, we see extraordinary economy in the model, the lambda CDM model, which just has 5 parameters describing all known phenomena at quite good accuracy already. So something is going on with fundamental physics, which clearly we're not fully understanding. And so I think it's a very exciting moment to have a seminar where we really attempt to renew the field of fundamental physics, come up with some genuinely new ideas, which are more predictive, let's say, than many of the fashionable paradigms, more predictive, more principled, and more basic. And so I really hope this seminar can be an example, not just of our solidarity with Ukraine, but actually an example in the world of theoretical physics to encourage radical new thinking. And I can think of no better way to, better sort of testimony of our belief in Ukraine and our belief in the future that we hold such a seminar based in Ukraine. So I'm delighted to see how many people have joined already. I expect there'll be more. And I really hope that the spirit and the atmosphere of this seminar will be appropriate, both for the solidarity and mutual support we want to show at this seminar with Ukraine, but also in terms of how strongly we believe in fundamental physics and encouraging people to come up with really new and interesting ideas. So thank you once again for attending, and I'm really looking forward to the first talk.
Thank you very much for kind words and for idea this seminar. Okay, and now also a few words from Stanislav Elginski, please.
Thank you, Sasha. I would like to say that the idea of creation of this seminar arose recently and belongs to Neil Turok and Mikhail Shaposhnikov. So I would like to express my deepest gratitude to Neil and Mikhail for organizing this series of seminars, especially at this difficult time when the bastard Putin and his fascist regime are trying to enslave and destroy our country, our Ukraine. So we all realize that not only modern, but also future scientific and technical progress of mankind is due to and largely based on the achievement of fundamental physics. It's true, it obviously. And of course, understanding and the achievement and challenge of modern fundamental physics and finding way of solving modern problem of fundamental physics play a crucial role for the future. The scientific experience and research result of all the speakers which are invited to participate in this series of seminars, without any doubts, will provide all of us with the opportunity to understand the perspective of modern fundamental physics and future. So, and I would like to wish of all us good luck in this way. Thanks.
Thank you very much. And now, after this opening part, I would like to introduce to you our today's speaker. This is Professor Astrid Eichhorn from the Center of Cosmology and Particle Physics Phenomenology of the University of Southern Denmark in Odense. Thank you very much for agreeing to give this talk. And let me say a few more words about our speaker. Astrid Eichhorn got her master's diploma from the University of Heidelberg and defended her PhD thesis at the University of Vienna. Then she was a postdoc at the Perimeter Institute for Theoretical Physics in Canada, and after that a junior research fellow at Imperial College of London. Okay. She was a junior research group leader in Heidelberg. And then finally, in 2019, she got an associate professor position in Center for Cosmology and Particle Physics Phenomenology, CP3 Origins, in Odense. Also, from 2018, she became a member of the German Young Academy and also belongs to the board of this academy. Professor Eichhorn won several grants and awards, such as Teaching Prize in Physics and Astronomy, Hans Berger Prize for Young Scientists, Sapere Aude Grant, and Willum Young Investigator Grant. Her research interests include from black holes and dark matter to particle physics such as Higgs sector of the Standard Model and beyond, UV completion of the Standard Model, and also quantum gravity and its interplay with matter. And today, Professor Eichhorn will tell us about connecting quantum gravity and particle physics. Why and how should one do this? Please, Astrid, the floor is yours. Thank you very much.
Thank you very much for this kind introduction and also for the invitation. It's indeed a great honor to open this seminar series, and I very sincerely hope that the seminar series will be successful in providing a platform to build new connections and to hopefully be a little bit of a building block to Ukrainian science in a hopefully soon to start peaceful future. So let me then share my screen to start the talk.
Yeah, maybe so, since we have a very big number of participants, maybe it is better to ask all questions in the end after the talk. Is it okay with you?
So for me, both versions are fine, but we can certainly have the questions at the end. All right, so what I will be talking about is the connection between quantum gravity and particle physics, and I first motivate why should we actually be trying to connect those two research fields, and then I'll talk about how to do that and what the tentative results of such a connection are. So first of all, let me start with the why, and let me briefly say a few words about each of the two research fields. So quantum gravity is trying to go beyond general relativity and understand the quantum structure of space-time. And so the questions that are being asked in this research field are, what is the quantum structure or the microscopic structure of space-time? How are space-time singularities resolved? What is the true nature of black holes? And other questions in this direction. And then in particle physics, we are trying to understand the Standard Model and go beyond the Standard Model to understand questions or find the answers to questions such as what is the nature of the dark matter, how do neutrinos acquire a mass, what determines the values of the couplings in the Standard Model, and questions like that. So at a first glance, these two research fields don't necessarily have a lot of overlap. So why should we actually be connecting the two research fields? And there are two answers to that, one on each side. So for quantum gravity, the answer is to make quantum gravity theories testable. That is, I would say, the major challenge in quantum gravity. There is a quite large number of candidate theories of quantum gravity. And one of the reasons why there are so many candidate theories and not one agreed upon theory of quantum gravity is because it's so difficult to actually connect to experiment. And of course, there are advocates that the connection to experiment should be given up completely, and we should just judge theories based on other criteria. I would advocate that in any natural science, the connection between theory and experiment is absolutely critical, and quantum gravity is no exception. And so we need to find ways how to understand the imprints of quantum gravity in experiments. And the challenge, of course, is that quantum gravity lives at tiny scales of 10 to the minus 35 meters or 10 to the 19 giga-electron volts, which makes this connection to experiment challenging. And as I will try to convince you, when we think about the interplay of quantum gravity with matter, this is where we can actually bridge this gap in scales between the quantum gravity scale and experimentally accessible scales, and where we can actually test quantum theories of gravity. So that's the first motivation. The second motivation is to also make progress in particle physics. So in particle physics, to answer many of those questions, one can write down phenomenological, to some degree ad hoc models or effective field theories. And there are many potential answers, for instance, to the question, what is the nature of dark matter? And I would advocate that in order to make progress in these fields and to actually select among the many phenomenological models that one can write down, thinking about more fundamental theories and the connection from particle physics to quantum gravity, that's a way how we can actually make progress and narrow down the many possibilities for answers to these questions here. And so in this talk, I will try to show you how establishing a connection to quantum gravity, to particle physics can make quantum gravity testable, but also how a connection to quantum gravity can actually select among the many phenomenological particle physics models and select just the few of those that are actually more promising from a fundamental perspective. So that what we then want to actually establish is a quantum theory of gravity and of matter together. And I'll be very conservative. I'll be trying to do that within the standard path integral formalism. So I aim at developing an understanding of the path integral over all metric configurations and all of the matter fields in the standard model, weighted by a quantum mechanical phase factor, where the starting point here, the action, is the Einstein-Hilbert action for the gravity part, and then the standard model action for the matter part, of course, coupled appropriately to gravity. And when we write down this path integral in such a way, then we are immediately facing two problems when we try to quantize it perturbatively. The problem of the gravity part is the perturbative non-renormalizability. So if we're calculating loop corrections here, we're encountering higher order counterterms, and they become of successively higher order in curvature as we go to higher loop orders. And that is actually a problem because predictivity breaks down, because each of those counterterms actually comes with a coupling that is a free parameter, and that would have to be fixed by experimental observations. There's no theoretical way of predicting that. And so if we go to higher and higher loop order, we are just increasing the number of free parameters that theory has, and so we are losing predictivity. Now, the matter part also has a problem, and that problem actually consists in Landau poles. So if we look at the couplings in the standard model that parameterize the various interaction strengths, and we follow their RG flow towards higher energies, some of those couplings, such as, for instance, the abelian gauge coupling, actually starts to increase and runs into a Landau pole. That, first of all, is just a signal that perturbation theory breaks down, but one can then use non-perturbative techniques, for instance, functional techniques or lattice techniques, to investigate those sectors of the standard model, and the conclusion that the theory breaks down at high scales actually persists. It is actually quite interesting where this breakdown occurs, because this breakdown that signals that there is some new physics that we are missing in the standard model, that breakdown occurs at a scale that is actually beyond the quantum gravity scale. And so if we are just looking at the standard model, and if we are asking the question, what does it tell us in terms of where we should be looking for new physics? The answer is we shouldn't be looking for new physics down here at LHC scales, but we should actually be looking for new physics beyond the quantum gravity scale. And so therefore, a very obvious candidate for what is actually missing in the standard model is actually quantum gravity. And what we then actually need in order to solve both of these problems is sort of a new ingredient in this quantum field theory. And what I'll be explaining to you is that a solution to both the predictivity problem in the gravity part and the Landau pole problem in the standard model part, the solution to both could be quantum scale symmetry, that's also known as asymptotic safety. And I'll take some time to introduce that idea. Just very briefly, why does quantum scale symmetry solve the predictivity problem? Well, whenever you impose a new symmetry, then you get new relations between the parameters in a Lagrangian or in an action, and that is actually the same for quantum scale symmetry. So as I'll explain, there are new relations that have to be obeyed in order for quantum scale symmetry to hold, and that actually reduces the number of free parameters to just a finite number. And then why is this a solution to the Landau pole problem? Well, what quantum scale symmetry actually means is that scale symmetry has to be realized. That means that couplings can no longer change as a function of the energy scale, but have to become constant. And if they become constant, that in particular means that they can no longer diverge. And this is how we are protected from Landau poles. I'll explain both of these points in a little bit more detail. So let me first take some time to introduce the concept of quantum scale symmetry. So quantum scale symmetry really is sort of the next step in following a success story of fundamental physics in the 20th century, namely the recognition, mainly based on Emmy Noether's theorem, that symmetries are really playing an absolutely crucial role. And so we know of quite a few different examples of both local as well as global symmetries in the standard model, and also in many, many attempts of model building beyond the standard model. The particular symmetry that I want to focus on is scale symmetry. And classical scale symmetry is, of course, also used quite extensively in model building. And scale symmetry, of course, just says that a system exhibits a certain form of self-similarity. So as I zoom in further and further, the system always looks the same. Now, what all of these examples for symmetries actually have in common is that they are typically imposed on the theory at the classical level. And then we're asking whether the symmetries persist at the quantum level or whether there are any anomalies. Now, scale symmetry here is particularly interesting because when we move from the classical theory to the quantum theory, the first thing that happens is that we typically actually lose scale symmetry, and that's because quantum fluctuations in general introduce a running or a scale dependence in the couplings. So the couplings of the theory start to depend on the energy or momentum scale. And so therefore I can very clearly always say what scale I am at just by looking at the different values of the couplings. So generically, scale symmetry is lost by going to the quantum theory. There's then a way of restoring classical scale symmetry, which is basically to switch off the effect of quantum fluctuations. And this is what you get when a theory is asymptotically free, so that the coupling approaches zero at very high energies. You're switching off the effects of quantum fluctuations, and you can get back to a sort of classically scale symmetric setting. That possibility is not available for gravity, simply because the Newton coupling has negative mass dimension, and therefore the Newton coupling can actually not become asymptotically free at high energies. And so this then leads us to ask whether there is maybe a more intricate version of scale symmetry that can be realized that really takes the quantum nature of fundamental physics seriously, and is a form of scale symmetry that really relies on the presence of quantum fluctuations. And there is indeed such a symmetry, so that is quantum scale symmetry, or also known as asymptotic safety. And what happens here is that quantum fluctuations actually balance out in such a way that couplings approach constant values. So interactions are still present, quantum fluctuations are still important, but nevertheless, scale symmetry is achieved because once the coupling becomes constant, obviously I can just zoom into higher and higher energies, and the interaction strengths always stay the same. And so that's the key idea of what asymptotic safety or quantum scale symmetry is. And clearly, if I can reach such a regime at high energies, then I'm obviously protected from Landau poles, or I'm protected from the theory breaking down. And a quantum field theory that realizes asymptotic safety is one that in principle can make sense up to arbitrarily high energy scales or arbitrarily short distances. Now, in quantum gravity, how this works is as follows. What we are looking at here is a dimensionless measure for the strength of gravity that I get by taking the Newton coupling and multiplying it by the energy scale squared. And this dimensionless measure, this dimensionless coupling measures how strong quantum fluctuations of gravity are. And if we are at scales somewhere in the regime of sort of LHC scales, so at the sort of GeV to TeV range, you can see that this dimensionless measure of the strength of gravity is really tiny, and that just tells us that it's actually a really good approximation to neglect the gravitational interaction at the LHC. However, this quantity then just increases quadratically as we go towards higher and higher energies. And the idea about asymptotic safety is that at the Planck scale, once quantum fluctuations of gravity are sufficiently strong, they can actually kick in to make this dimensionless version of the Newton coupling constant. And that's encoded in this beta function, so the scale derivative of the Newton coupling, which has a term that comes from canonical scaling and a term from quantum fluctuations. And you can see these two can balance out and give you a vanishing beta function, which translates into a constant coupling. And indeed, in pure gravity, there is a lot of theoretical evidence that gravity does behave in this way. There are some open questions, most importantly among them unitarity and Lorentzian spacetime signature, but there is also a more recent progress that shows that these could actually be compatible with asymptotic safety. Now, before I move on to talk about the interplay with matter, let me very briefly also say something about the tools that one can use to search for asymptotic safety. The tool that is most commonly used is the functional renormalization group. That is a technique that can be very widely used in quantum field theories, from quantum gravity through particle physics to condensed matter and statistical physics. And loosely speaking, it's a mathematical version of a microscope. As a function of the RG scale K, which is an energy or momentum scale, it allows to scan sort of through a theory from the ultraviolet all the way to the infrared, and successively account for quantum fluctuations as a function of that energy scale. More technically, it provides us with a functional equation from which we can extract all of the beta functions in the theory. So those are the scale derivatives of the coupling. And with that, we can then do two things. First of all, we can search for whether or not there is scale symmetry. And we do that by calculating the beta functions and then look for zeros of those beta functions. And those give us such a quantum scale symmetric regime. But then, of course, the thing that we crucially want to do is to connect this regime beyond the Planck scale to scales where we can actually connect to experimental data. And one can also do that here by numerically integrating those beta functions to obtain the coupling as a function of the scale. All the statements that I will be making in this talk are based on this technique. As any quantum field theoretic, or most quantum field theoretic techniques, it actually relies on approximations or expansion schemes. So specifically here, I will be using truncations of the full dynamics and will in many cases be neglecting higher order operators, which actually means that there are systematic uncertainties in the results that I will be presenting. So one of the really crucial things about quantum scale symmetry is how it actually allows us to make predictions, in particular predictions in particle physics. And that actually relies on the effect that quantum fluctuations have on interactions, so they can either screen or anti-screen interactions. There are standard model examples for both. For instance, in QED, the fluctuations of charged fields actually screen the coupling, and that's encoded in a positive leading order coefficient of the beta function. And that positive coefficient means that the coupling decreases as the energy scale is lowered. That just means that quantum fluctuations screen the electric charge. We have the opposite behavior in QCD, where the leading order sign is a negative one, and that actually means that the coupling increases as the scale is lowered, so quantum fluctuations anti-screen the interaction. And now, if I'm going to asymptotic safety, these two effects, screening or anti-screening, can be combined in two different ways. And in this way, I can actually get interactions which remain as the free parameters of my theory, or interactions which correspond to quantities that can be predicted. So specifically, if I have a coupling that becomes asymptotically safe, so its beta function has a 0 at this particular value alpha star, then here I am showing you an example where the leading order coefficient is positive, so screening, and then the second coefficient that becomes more important at higher values of the coupling is anti-screening. And that actually means that if I just depart a tiny little bit from scale symmetry towards lower values of the coupling, then the screening effect kicks in and drives the coupling towards lower and lower values. And if I depart just a little bit towards larger values of the coupling, then the anti-screening quantum fluctuations become important and drive the coupling towards larger and larger values. And that actually means that if I start from scale symmetry in the very, very far UV, then I can actually reach a whole range of these coupling of the values of the value of this particular coupling at lower scales. And so this means that starting from scale symmetry, I cannot predict what the value of that coupling is. So it remains a free parameter of the theory. And now the more interesting case is obviously the opposite case, where I just switch the two signs. And so the leading order coefficient is now an anti-screening one, and the higher order coefficient is a screening one, because in this way, whether I depart towards larger or smaller values than the fixed point value, quantum fluctuations always drive me back towards scale symmetry. And that actually means that if I start with scale symmetry in the very far UV, I'm just remaining at this fixed point value of the coupling all the way to lower scales. And that means that starting from scale symmetry in the very far UV, I'm getting a prediction for the value of the coupling at low energies. And so these are the couplings that we will be particularly interested in, because for those, if we have scale symmetry beyond the Planck scale, we can actually make predictions for couplings at lower scales. Now, what is the situation like in pure gravity? Here the dynamics and asymptotic safety includes an Einstein-Hilbert term and then higher order gravitational couplings. And I'm just showing you some selected examples from the overall quite large literature. And the situation here is that the three first couplings, namely the Newton coupling and the cosmological constant, and then also a superposition of the two curvature squared couplings, those correspond to the ones that are the so-called relevant couplings, the free parameters of the theory. And then all of the higher order couplings, their values are actually fixed by scale symmetry, which solves the problem that a perturbative quantization of gravity has, namely this predictivity problem. It also means that in principle, there is a lot of ways in which asymptotic safety can be tested, because the values of all of these higher order couplings are actually predicted or fixed. In practice, that is not very useful though, because in practice, of course, an experimental test that would actually constrain or even measure the value of something like this curvature cube coupling, that is just experimentally not feasible, not even in the strong gravity regime that we now have observational access to with black holes. So this means that quantum scale symmetry has predictive power in pure gravity, but we can't make use of the predictive power because our experimental observations are just not sensitive enough. And this is where the connection to particle physics becomes important, because in particle physics, the situation will be different. Those couplings that are predicted by this setting are actually couplings that we have experimental access to, and that where we can compare the predictions to experimental results. And so now I'm at the point where I couple quantum gravity to matter, and then such an asymptotically safe quantum gravity matter theory actually has three regimes. At very high energies, so beyond the Planck scale, there is quantum scale symmetry, which means that the couplings either are constant, so asymptotically safe, or they decrease towards zero. So some of the couplings in the very, very far UV just become zero, so become asymptotically free. And then what happens at the Planck scale is that quantum fluctuations of gravity decouple, and that's encoded in this dimensionless Newton coupling that I showed you previously, where I told you that actually below the Planck scale, it actually decreases quadratically. So this means that at the Planck scale, we have a very swift transition from a theory where quantum fluctuations of gravity are important to a setting where quantum fluctuations of gravity have turned off, so to say, or have become so tiny that we can neglect their effect. And so then below the Planck scale, we are just back in a setting where we just have a scale dependence of the couplings just driven by the quantum fluctuations of matter, just as we know it in the standard model. And now one of the important things about this whole idea is that some of the couplings in the standard model become these so-called irrelevant couplings of that setting, which means that their values at the Planck scale are actually fixed uniquely by asymptotic safety. And that actually means that I can provide an initial condition for the scale dependence of those couplings at the Planck scale, and then one can just use standard renormalization group techniques to calculate what is the corresponding value at, let's say, LHC scales. And the first such example actually comes from one of the organizers of this seminar, namely Misha Shaposhnikov, together in collaboration with Christoph Wetterich, where they proposed that the Higgs-quartic coupling could actually be one of those couplings that is fixed by asymptotic safety. And so their prediction in 2009, so predating the actual measurement of the Higgs mass, actually came tantalizingly close to the value that was then measured. Subsequently, it was found that also some of the other couplings in the standard model could actually become predictable or calculable quantities. So that would, for the first time, actually give us a first principles calculation of those couplings. But it also means that quantum scale symmetry beyond the Planck scale becomes testable by calculating the values at lower energies when we can compare to experimental data. And I now spend some time to explaining these ideas to you, and then towards the end of the talk, I'll talk about how to go beyond the standard model and address some of the open problems or questions beyond standard model particle physics. Let me actually skip this slide here and go directly to the quantum gravity effects on the standard model, where I'll start with the gauge sector. So what we have is just the standard beta function for a gauge coupling. Just the leading order term starts with the gauge coupling cubed, and the one loop coefficient depends on whether we are looking at an abelian or a non-abelian gauge coupling. And then when we add quantum fluctuations of gravity, something interesting happens, because a new linear term actually shows up. And that term actually is the same type of term that we would get if we would change the space-time dimensionality away from 4. We would also get a linear term like that. And so an intuitive way to think about the effect of quantum fluctuations of the metric is that they introduce something like an effective change in dimensionality. So a quantum field theory of matter that is coupled to quantum gravity effectively perceives something like a changed space-time dimensionality. So the quantum gravity effect is actually encoded in this FG. That FG is just a shorthand for a longer function that depends on the gravitational couplings that I'll just flash very briefly here. It is actually independent of the gauge group, and that is because gravity doesn't care about whether it couples to an abelian or a non-abelian gauge group and what the gauge group actually is. So very intuitively speaking, gravity doesn't see whether it's coupling to a photon or to a gluon. It's blind to these internal symmetries. It just sees that it's coupling to a gauge field. And so therefore this FG is universal for all gauge groups. The crucial point about it is that it's constant in the scale symmetric regime above the Planck scale, and that it goes to 0 below the Planck scale. There's a more technical comment on this FG that relates to how calculations in various schemes actually relate to each other, and whether this quantity is actually universal. So I'm not going into details here. If you're interested in this more technical comment, you're very welcome to ask me in the question session. Now, the crucial thing that happens because of this quantum gravity contribution is the following. When we are looking at the non-abelian gauge couplings, so the QCD coupling and the SU2 coupling, because there is a negative sign here, it means that asymptotic freedom that we have in those gauge theories anyways, that is preserved under the coupling to quantum gravity. So quantum gravity doesn't destroy the fact that these quantum field theories are already UV complete. And something very interesting then happens for the abelian gauge coupling. So for that, the one loop coefficient is actually positive, and that actually leads to a Landau pole in the abelian gauge coupling. And now when we switch on quantum fluctuations of gravity, we're actually getting a competition between this one loop term and between the quantum gravity term. And this competition means that if we're in a regime where gravity dominates, so at small enough values of the gauge coupling, then this negative sign here plays an important role, and the gauge coupling is just driven towards asymptotic freedom. Conversely, if we're in a regime with large values of the gauge coupling, then this one loop term here wins, and then we are still encountering a Landau pole. And those two effects can actually balance out at one specific value of the gauge coupling that gives us asymptotic safety. And that unique value for which we get asymptotic safety actually translates into a unique value that we get in the infrared. And as you can see in this plot here, this infrared value also serves as an upper bound on values of the gauge coupling, because for any lower value of the gauge coupling under the effect of quantum gravity, the gauge coupling becomes asymptotically free. So the theory is also UV complete and safe from Landau poles. But for any value of the gauge coupling that is larger than this special value, you're still encountering a Landau pole in the UV. And so this means that if asymptotic safety or freedom holds, then there is an upper bound on the value of the gauge coupling. Or in other words, from this specific asymptotically safe fixed point, you get a unique prediction. Now, the same type of pattern actually holds in the Yukawa sector. So again, we are getting a contribution from quantum gravity that is actually linear in the Yukawa coupling, and this Fy is again a longer function of the gravitational couplings that I will not show here, where again the crucial feature is that it's constant above the Planck scale and it drops to 0 below the Planck scale. What is really interesting about the Yukawa sector, though, is that this Fy can have different signs depending on the values of the gravitational couplings. And if we first look at the situation where the Fy is negative, then this actually means that both of these terms here in the beta function are positive, which actually means that that any value of the coupling that is larger than 0 will actually lead into a Landau pole. Or said in a different way, the only way to get scale symmetry is to set the coupling to 0 beyond the Planck scale. And once you have set a Yukawa coupling exactly to 0, it will just stay 0 all the way into the infrared. And so if Fy is negative, that actually means we're getting the prediction that the top Yukawa coupling actually vanishes exactly. And now the LHC has already measured some of the Yukawa couplings in the standard model, not all of them, but the top Yukawa coupling is one of those, and it has been measured to be non-zero. And so if we are in a regime where Fy is negative, then that actually means that the measurement of the top quark Yukawa coupling at the LHC, that would actually rule this theory out. Now, before I tell you what the sign is that is most likely realized, let's take a look at what happens if the other sign is realized. So if Fy is larger than 0, then we're again getting the same type of dynamics as in the gauge sector, namely a competition between matter and gravity fluctuations, and that those two actually balance out at an asymptotically safe fixed point, which serves as an upper bound for the allowed values of the top Yukawa coupling. And now, of course, the question is, what is actually the value of Fy in asymptotically safe gravity? So first of all, Fy depends on the gravitational couplings. So it depends on the microscopic value of the Newton coupling and the microscopic value of the cosmological constant. There is this border here between the regime where Fy is negative, and we would get the prediction that, for instance, the top mass vanishes, and then this regime where Fy is positive and the top mass can be larger than 0. And now we can calculate where the gravitational fixed point values fall. And if we add just one generation of matter, then they are actually quite deep within this regime where Fy is negative. And then the gravitational fixed point values actually depend on matter. And as we add a second generation, they move a little bit, but they're still in this regime where Fy is negative. And then in this paper here, in the approximations we used there, what we find is that the fixed point value actually moves into this regime where we're getting a non-vanishing top quark mass as soon as we add 3 generations of standard model fermions. And so that hints towards quite an interesting interplay between quantum gravity and matter, where gravitational couplings have to have certain values in order for the matter sector to be similar to the standard model. And then indeed, quantum fluctuations of matter actually drive the gravity theory into this regime that is needed. Now, let me also comment very briefly on extensions beyond the top quark. So let's look at the top-bottom system. And of course, one of the questions there is, why is actually the bottom mass different from the top quark mass? And indeed, this paradigm of asymptotic safety could potentially provide an explanation. And if we're looking at the top and bottom Yukawa couplings, they're actually quite similar. In particular, the gravitational contribution to both of them is the same because gravity is blind to flavors. So gravity is not aware whether it's coupling to a top or a bottom quark. However, what distinguishes the top and the bottom is actually their hypercharge, their abelian hypercharge. And so as soon as the abelian gauge coupling is non-zero, then the fixed point values for the top and the bottom are different from each other. So we're getting a fixed point relation that relates the microscopic value of the top and the bottom quark to the microscopic value of the gauge coupling. And you can see that as soon as the gauge coupling is non-zero, as it can indeed be in asymptotic safety, then the top quark is generically has a larger Yukawa coupling than the bottom quark. And indeed, as a function of these two parameters, Fy and Fg, that enter these two beta functions and that parameterize the gravitational effect, there is a point in this parameter space where the low energy values of the top and the bottom quark and the abelian hypercharge fall close to the standard model values, not exactly on top of the standard model values. The top quark actually comes out about 10% or so too heavy. But you have to remember, of course, that this is also a rather simple approximation for the full system. So indeed, setting Fy and Fg to these preferred values then gives you an asymptotically safe regime above the Planck scale, and then below the Planck scale, something that actually looks tantalizingly close to the standard model, with just the top Yukawa coupling being somewhat larger than it is in the actual standard model. And so when we summarize the quantum gravity effects on standard model couplings, it appears to be possible to make retrodictions of some of these couplings. They are not predictions because the couplings have all been measured. Those retrodictions are subject to quite large systematic uncertainties at the moment. And within these uncertainties, we're seeing sort of standard model-like structures. And so what I would say is that we've sort of scratched the surface of these type of ideas, and it currently remains to uncover whether we are actually looking at some really interesting structures, or maybe we have just we've just found something that isn't so interesting after all. And so one way to find out whether what we're looking at is actually something really interesting and whether these ideas could really be realized in particle physics or not, one way to do so is to actually go beyond the standard model, because of course we do need physics beyond the standard model to explain all of the observations. And so the question here then becomes, which of the many, many models that one can write down to explain physics beyond the standard model, which of those are actually compatible with asymptotic safety? And I take about 5 to 10 minutes or so to talk a little bit about these ideas. So the first type of physics beyond the standard model that I'll be looking at is neutrino masses. And neutrinos, as far as we know, have really tiny masses at the microelectron volt scale. Those masses can actually be accommodated if we're just adding right-handed neutrinos to the standard model and if we introduce neutrino Yukawa couplings. However, in order to produce these very small neutrino masses, those Yukawa couplings have to be set to quite small values. Of course, there is already a hierarchy between the Yukawa couplings of the quarks and the leptons in the standard model. But for many people, this additional hierarchy towards the neutrino Yukawa couplings is sort of too much of fine-tuning, and therefore alternative ways of mass generation, for instance, seesaw mechanisms have been developed. So here I'll be much more conservative or minimalistic, and I'll really just add the right-handed neutrinos to the standard model and add these Yukawa couplings, and then I'll be interested in whether this regime of very small neutrino Yukawa couplings can somehow be reached. And so for that, we're again looking at the beta function, which has a quantum gravity contribution as all of the other couplings. But the really crucial thing here is that there is also a big contribution from the top Yukawa coupling. as soon as you set the top Yukawa coupling to this non-zero fixed point that I've been talking about previously, it actually dominates in this beta function. And so then there is a positive term that dominates, which means that the neutrino Yukawa coupling is then driven towards smaller values. So what I'm showing here is a system where at really, really high RG scales, I'm actually starting at asymptotic freedom for all of the couplings, and then they all start to increase. In particular, the top Yukawa coupling increases, and then for a large range of scales is actually quite close to this asymptotically safe fixed point value. And as soon as the top Yukawa coupling is close to that fixed point value, it drives the neutrino Yukawa coupling towards smaller values. And what that means is that asymptotic safety could actually accommodate or even dynamically provide a reason why the neutrino Yukawa couplings should actually be as small as they are. But it also means that these small neutrino masses can be accommodated in an asymptotically safe model of gravity and matter just by adding Yukawa couplings. There is no need for further extensions of the standard model in that setting. So for the final bit of physics beyond the standard model, let me actually talk about the dark sector, and specifically just the dark matter sector that is, as far as we know, not explainable by standard model physics. And so therefore, there's just a huge parameter space or space of effective field theories of phenomenological models that spans many, many orders of magnitude in interaction cross-section and also in masses, with various proposals all over the place. And so what I would advocate is that what we need here is some theoretical idea that allows us to sort through many of these proposals and to find out what is actually what are actually the more promising ones. And I'll be advocating that asymptotic safety is actually a possibility to do better and to go beyond this huge space of phenomenological models and actually to rule out many of those and narrow down the possibilities for what explanations of dark matter could be. And I'll provide two examples that give a proof of principle for the predictive power and show you how dark matter models could actually be ruled out by asking whether or not they can become asymptotically safe together with quantum gravity. And the simplest example for that is the vanilla model of dark matter, which says that dark matter is just a singlet scalar, phi, that it couples to the standard model through a Higgs-Portal coupling. That Higgs-Portal coupling allows dark matter to be produced in the early universe. And it also provides a channel for direct searches, both at the LHC as well as at experiments such as Xenon. And through those searches, actually, the parameter space for this vanilla model has already been reduced quite a lot. So if we look at the space of Portal coupling versus mass, then most of this parameter space has already been ruled out, and there are just these small slices of the parameter space that are still remaining. Now, what happens if we add quantum fluctuations of gravity to that setting? We're again getting a contribution of quantum gravity that is linear in the coupling, where this F lambda again parameterizes the effect of quantum gravity fluctuations, and that F lambda turns out to be positive. What that actually means is that quantum gravity fluctuations drive the Higgs-Portal coupling towards zero at the Planck scale. So even if you were to start with a non-zero Higgs-Portal coupling, quantum gravity fluctuations would drive it to zero. And once you've set the Higgs-Portal coupling to zero at the Planck scale, it's also not regenerated at lower energies. And so therefore, the Higgs-Portal coupling just vanishes in asymptotic safety. So a single dark scalar would decouple. And that would mean you can't produce it through the standard thermal freeze-out, and you also cannot find it through direct searches. And so in that sense, the fact that this parameter space has just narrowed down more and more in the experimental searches and no detection has been made, that you can, if you want, view that as an encouraging sign for asymptotic safety. One can then actually go beyond and try to build extended dark sectors with not just a singlet scalar, but also a dark fermion. And I don't want to go into many details here. I just want to briefly say that such a dark sector, if it is an effective field theory, it actually has quite a few free parameters. and so it would have quite a large parameter space. But if you want to make such a theory asymptotically safe as it is coupled to quantum gravity, there's actually just a single free parameter that remains. And that means that all of these couplings in the theory, the masses of the dark scalar and the dark fermion, the Higgs-Porter coupling, the scalar self-interaction, and also the mixing angle to the Higgs, all of those are related to each other. And this huge 6-dimensional parameter space just collapses to a single line. That doesn't necessarily mean that I want to advocate this type of model as a viable model of dark matter. I view it more as a proof of principle that asymptotic safety really has a lot of predictive power because it can reduce these huge parameter spaces to much, much smaller parameter spaces. So that's the story on asymptotic safety and sort of WIMP-like dark matter. So you see that a lot of possibilities seem to be ruled out here. And there are, of course, then other suggestions for dark matter. One that is maybe quite popular at the moment it consists of axions and axion-like particles. And so very briefly, axion-like particles are pseudoscalars, so they can couple to this combination of the electromagnetic field strength and its dual through this axion or ALP photon coupling. That field then, or that particle has an interesting phenomenology because it can provide an ultralight dark matter candidate. And this coupling to photons actually gives rise to very interesting possibilities to search for experimentally, namely by converting a photon into an ALP in a magnetic field. And that ALP is then very weakly coupled to matter, so it can traverse through a wall. Behind the wall, you have another magnetic field in which the photon is being regenerated. And so you have shown light through a wall. So that's one of the main ways to search for ALPs. Now, what's the story of ALPs and asymptotic safety? When we look at the beta function of this ALP photon coupling, there is a quantum gravitational contribution. However, you can see that the other terms in this beta function are actually both positive. And so the only fixed point for this coupling is 0, unless this Fg is actually large enough to overwhelm the leading order term. And if this Fg, this is the quantum gravity contribution, is large enough, that means that quantum gravity would have to be quite strongly coupled. So we can see this if we look at the plane spanned by the microscopic gravitational couplings. This shaded region here is the region where the Fg would be larger than 2, and you can see it lies at quite large values of the dimension as Newton coupling. There's a longer story to be told here, where there is what we call a weak gravity bound, not to be confused with the weak gravity conjecture, that actually makes this region very likely unviable. But also if you calculate where the gravitational fixed point values appear to lie, they lie somewhere here, quite far away from this region here. And so what we are concluding is that there are no ALPs in the asymptotically safe landscape. And also this model for dark matter is actually one that doesn't appear to be compatible with asymptotic safety. So another example for how the predictive power of asymptotic safety actually can rule out a model that, as an effective field theory, would provide a compelling explanation of dark matter. And so that already actually brings me to my summary. So I hope I could convince you that the connection between quantum gravity and particle physics makes sense, both because it could provide us with tests of quantum gravity, but also because it has potential predictive or explanatory power for particle physics, and it could provide us with ways to calculate some of the free parameters of the standard model. And as an example, I've talked about how the abelian gauge coupling is bounded from above and the top Yukawa coupling is bounded from above. And then also beyond the standard model, how neutrino Yukawa couplings are driven towards 0, as well as quartic couplings, and also the ALP photon coupling. And as an outlook, of course, there are two main things to do here. The first is to reduce the theoretical uncertainties and to narrow down the theoretical uncertainties so much that we can really meaningfully compare the predictions to experiment and say whether or not asymptotic safety is experimentally viable, but also to go beyond the standard model and understand what is really a complete model of particle physics that can actually explain all of the various observations, but that is also compatible when it's coupled to quantum gravity. And with that, I'd like to thank you for your attention, and I'm looking forward to questions. And for those, I'll stop the screen share.
Thank you very much for a very interesting talk. Okay, so now we turn to the questions and answer sessions. We strongly encourage young people, undergraduate, PhD students, postdocs, young scientists to ask questions. And please, so first question is from Sebastian Zell. Please unmute yourself and ask.
Yeah, thanks a lot for this very nice talk. So if you'd allow, I'd like to ask two questions. So the first one is about the dark matter. So you said that there are such scenarios that are very constrained. Is there like a preferred scenario from your point of view?
So that's a great question. We're actually still looking for one, because as you saw, the simplest explanations, namely just a simple dark scalar, or also just an axion-like particle, those appear to be ruled out. We're still looking through the space of possibilities to find what sort of the preferred scenarios. I think Neil has a very interesting suggestion for what dark matter could be, namely there's the right-handed sterile neutrino, and that would be something that could potentially be accommodated in this setting because of this property that the neutrino U-Carver couplings are driven to zero. But whether or not that really works out with the standard model is an open question at the moment.
Okay,
but there might then really be a minimal explanation of dark matter that fits into the paradigm.
Yeah, thanks a lot. So yeah, if you allow me to continue, so about the unitarity that you discussed in the beginning. So naively, if I look at an R-squared term, then I would say, okay, this is a new propagating degree of freedom that is healthy, that can be the inflaton. If I look at the R mu nu squared, then at first sight I would think there's a ghost. So what's the story there?
Yeah, so the main point is that if you just add higher order terms up to a finite order, then generically it's true that those will introduce additional propagating degrees of freedom, and those are typically not healthy. So you're typically getting ghosts. That story, however, is different if you really have terms up to arbitrary high order. So if you really have a function of the curvature terms that doesn't stop at a finite order in the Taylor expansion. In some of the references I mentioned, people have constructed explicit examples where such higher order terms are present, and the theory is nevertheless healthy. And there are indeed indications from explicit calculations of the graviton propagator and asymptotic safety that don't show any indications for any additional poles.
All right, and so it would really be the massless graviton that propagates, or are there additional healthy degrees of freedom?
So in those settings that where people have looked at explicitly, in this one paper, more recently at the graviton propagator, they're only finding the massless graviton pole.
All right, thanks a lot.
Okay, thank you, Sebastian. And now we have a question from Vladislava Sharkovska.
Hey, Astrid, thank you a lot for this inspiring talk. I was wondering about this particular question. What are the challenges to describe RG-improved Kerr black holes? Like, for example, the problem inside the Cauchy horizon, maybe?
Yeah. So indeed, one of the obviously interesting questions to ask in this program is what happens to black holes. And as you've mentioned, what people mainly do is to RG improve. So they start with the classical line element, and then they take the scale-dependent Newton coupling and identify the RG scale with a curvature scale in the setting. And indeed, if you do that for a Kerr black hole, you're getting a setting which has gotten rid of the curvature singularity in the center. So it's a regular black hole, but the Cauchy horizon persists. Whether that is then unstable and on what timescale and so on, that is actually not fully understood yet. So I would say the final answer of what a black hole really looks like in asymptotic safety, we're still working on that. But I think the main takeaway message so far is that asymptotic safety is able to lift the curvature singularity. And understanding the Cauchy horizon, that is really a more tricky question then.
Okay, I understand. Thank you.
Much. Please, colleagues, who else wants to ask a question? Okay, we have a question.
Questions. Sorry if I interrupted. So
Okay,
I would like to ask, this as to your knowledge, are there any, how to say it, can we test this scalar invariance idea via astrophysical observations, specifically of very massive like lasers, EGNs, etc.?
I would expect that that's definitely not straightforward to test those, because the energy scales that are reached are typically still below the Planck scale, right? I mean, if the transition scale to the fixed point regime, if that is somewhere where experiments can reach, then you can really see scale symmetry explicitly in the scattering cross sections. But even astrophysically, the energies that are reachable are typically not high enough. And now whether modifications to sort of space-time metrics of these objects are large enough in order to really leave an imprint in observations, and whether you can disentangle those effects from sort of the messiness of astrophysics, that is a very tricky question, and it's, at least to my knowledge, there isn't any proposal that is really possible. Supermassive black holes potentially might be a slightly different story, but also there, disentangling the effects of space-time modifications from the effects of the astrophysics that goes on around these objects is just really tricky.
Thank you for your answer.
thank you. So the next question is from Yuri Shtanov.
Okay, thank you very much for your very interesting talk. Astrid, I wonder whether I understood you correctly, that you have to deal with the infinite number of gravitational Lagrangians of high and high order, right? Every one of them has a coupling constant. So does it mean you have to deal with infinitely many coupling constants at the same time? How can you cope with them? If not, then what happens to this infinity? So, and if this is correct, so does it mean that your theory actually in the ultraviolet becomes non-local?
So you've understood correctly that all the higher order curvature terms become important potentially and have to be included in studies. Now the technique that I talked about very briefly, the functional renormalization group, that actually allows to do both polynomial expansions to finite order, but it also allows to look at really functions of curvature terms, where you're encoding an infinite series of coupling constants in one function. So the technique actually allows you to deal with infinitely many coupling constants all at once. Now let me quickly remember what was the second question. Oh, whether the theory is non-local.
Yeah.
So I think whether the answer is yes or no depends on what you mean by non-locality. So in the UV, certainly higher order curvature terms are present, but they are all sort of quasi-local terms. So they are all positive powers of derivatives. What is not present in the UV is something like 1 over box or 1 over curvature terms. So this type of non-locality is not present in the UV. That is generically, as in any effective action, generated in the infrared, but that is of course a whole different type of problem. So in the UV, it's just positive powers of derivatives which are present.
All right, thank you.
Thank you very much. Okay, the next question is from Василь Шендеровський.
Доброго дня. Пане Олександре, я вас попрошу допомогти мені коротеньке, просте питання. Перекладіть, будь ласка, тому що буде погана англійська мова.
Just one moment. Excuse me, please, Astrid. I will translate you the question from Ukraine, okay?
Yeah.
Так. Дуже гарно дякую за гарну доповідь. І я колись займався також флуктуацією на твердотільній плазмі. Питання моє таке. У вас багато в вашу теорію входить констант, різного роду констант. Це один із ваших висновків, які ви зробили в своїй доповіді. І ви сказали, що ці константи можуть бути визначені із експериментальних даних. У мене питання, коли і які ці експерименти можуть бути здійснені, щоб мати ясну картину щодо тих констант, які введені в теорії? Дякую.
Дякую вам за запитання. So the question is, so first of all, Vasil thanks you very much for such an interesting talk. And he asks the following question. So you have a lot of coupling constants in your theory, and they should be somehow tested experimentally. Which experiments in the nearest future, maybe you can name some experiments, which can be used to fix these constants in your model?
Thanks for the question and also for translating. The meta part of the theory that contains the same coupling constants that we always had in the standard model, and that of course we already have measured experimentally. And the thing that is missing in the standard model is a theoretical calculation, right? In the standard model, they are all free parameters. And so what this theory could provide is a first principle calculation of some of those free parameters, not all of them, some of them remain free parameters. And then the experimental data that has already been collected for decades and decades, right? So we already have the experimental data in order to test the theory. What we need to do is to make the theoretical predictions more precise. And then, of course, there are also couplings in the gravitational sector that have not yet been measured, like the higher order curvature terms. And there is potentially the possibility to constrain at least the curvature squared couplings from strong gravity observations. But presumably those will only give rise to upper bounds, which are still quite large. So if those couplings are really of order 1, as the indications are, then I don't see any way of testing that experimentally. So instead, what we have to rely on is really the data that we already have in particle physics. And of course, if physics beyond the standard model is discovered, let's say there is dark matter that is discovered, then that provides new couplings where we can again check whether they are compatible with these ideas or not.
Thank you very much.
Дякую.
Okay. Who else wants to ask a question? Okay, we have Volodymyr Krasnogolovets, please.
Yeah, my questions was before Vasil Shenderovsky, but it's exactly follow Vasil Shenderovsky. The point is that typically people who are working in fundamental physics, they use not mathematical physics, but physical mathematics, which are very different things. And then following, then try to using equations of physical mathematics, try to apply them to real things like experimental investigations, to find some parameters, to calculate something, to compare something, the calculations with real things. But real things, once again, can be described only using mathematical physics. And this is a problem with Higgs boson. If you read a paper of 1966 of Higgs, you will see that he operates only with fields which do not have any real characteristics, and obtain something. And they, having this something, we try to apply to real things, to find something in experiment. It's very difficult things. And many people who operate, practically all, maybe I know 99 and 99% of people who work in fundamental physics, it seems to me, do not understand these things. I'm working also in fundamental physics and have some serious results, but I operate only in the framework of mathematical physics. And that is why my results is very different from all other people, but at the same time, they have quite serious applications.
Could you please
What do you think? How you can compare your calculation? Just a moment. How you can compare your calculation based on physical mathematics with real mathematical physics?
So So I'm not sure I'm understanding the question correctly, but the way that I would rephrase it is to say that of course the challenge in such theories is that real physical observables are quite difficult to construct, mainly because of the gauge symmetries that we have in those settings. And for instance, in quantum gravity, if one goes into the sort of really deep and non-perturbative quantum gravity regime, then observables will be generically non-local and not things that we have actual access to experimentally. So I would say the way out of this challenge is that fortunately experiments don't seem to apply to a sort of deep non-perturbative quantum gravity regime, but to a regime of quantum gravity where we essentially have something that is close to space, flat space-time with very small fluctuations. And in that setup, this challenge of finding out what are the observables of the theory reduces quite a lot, and then something like scattering cross sections of particles do become actual observables of the theory, and one can really prove that precisely that those then become gauge invariant observables. And of course, the couplings that I've talked about are not observable quantities themselves, but again, they are quantities that enter physical observables in a particular way, and so we then know which values of the couplings are required in order for a particular cross-section to come out in agreement with the experiment. So there are, of course, a number of steps that sort of happen on the way to the connection of experiment.
You use many fitting parameters. For example, usually mathematical physics is operating with real fields. For instance, we investigated wave equations. We understand what happened. What does it field in these calculations? This is a contraction and in one aspect and something spreading and contraction. But when you operate as a field of contraction, when you operate with physical mathematics, we do not understand what kind of field you use. As a phi, for instance, phi or something else, but no real applications to something. It's abstract waves, abstract parameters, completely abstract parameters. How you can try to apply it to real things?
So I agree that the fields that we work in, that we work with, of course, don't directly correspond to anything that has physical reality, because they are gauge fields, right? And of course, something like the path integral is a quantity that is mathematically incredibly ill-defined.
One more. You talking about symmetry. You use symmetry, but the symmetry, if you come back to the end of 19th century, studies of Riemann and for instance, Helmholtz, they showed that when we can apply symmetry, only when we consider the particle like a very rigid object. In this case, we can introduce some symmetry. And this immediately we can decrease a number of equations, which is the described particle to only a few equations. But if the particle is not rigid, you cannot introduce any symmetry. But all physics now, physicists operate not only with this idea that the particle is rigid, but they consider particle as a point. Fantastic story. What do you think about it? We know that G.G. Thomson showed that electron has some size more than 100 years ago. 100 years ago, also Compton showed that particle has some rigid radius of rigidity. And this means that they have size. But modern particle physics used only a point, and in this case, we can, of course, imply different kind of symmetries.
Yeah, I mean, so all of the
inside of theories,
we are running out of time. Could you please then maybe we can move this discussion after the official part of this talk, okay? because you asked too many questions, and we have other people which also want to ask questions.
Okay, if you don't mind, I will communicate with you personally through electronic.
Yeah.
Yeah, sure.
Be perfect. Yeah, thank you very much. And okay, who else wants to ask a question? Yes, Stanislav Elginski. Ah, yeah. So sorry, excuse me, Valery Pavlovich, you will be the next.
Oh, okay.
Okay, Stanislav,
thank you.
You raise the hand.
Yeah, thank you. If I understand it clearly, thank you so much for your talk. If I understand it clearly, we include in our theory an infinite number of terms with positive degrees of curvature, and I'm going to ask how are we maybe confident that it not violates our previous calculations with just R in action, so like the Eddington experiment or something like that. Yeah.
Yeah, so I think that there are two answers to that question. One is sort of whether we are sure that a theory with higher order terms fits observations, and the answer is as long as those couplings with higher order terms are not extremely large, then all our observations are at low enough curvature that those higher order terms are just observationally completely irrelevant. The other aspect of higher order terms is actually a control over the calculations. So the question, if I'm doing these type of calculations here and I'm just including a subset of the higher order terms, how do I know that terms of even higher order that I haven't included will not spoil the theoretical results here? And there is, of course, not a way to prove that something like asymptotic safety really exists in those theories. So there is only accumulating evidence in successively higher and higher orders. But there is a very vast literature that goes these steps to include higher and higher and higher order terms. And one can indeed see an apparent convergence of the results where the higher order terms become successively less and less important, and the results established in previous approximations sort of carry over.
Yeah, thank you. Thank you so much.
So now, please, Valery Pavlovich Husenin.
Thank you very much for your interesting talk. My question is purely technical. You show us some expression for beta functions. We see there one loop correction, usually one loop correction, for example, electrodynamics and quantum chromodynamics, and the next term comes from correction due to gravity. And the question is how these corrections looks in terms of Feynman diagrams. Is it due to change of one graviton or due to change of many gravitons? A so-called addressed graviton propagator.
Yeah. So in terms of diagrams, you can basically think of the gravitational contribution as a one loop contribution as well. But the way that the functional renormalization group is set up is actually somewhat different from the Feynman diagrams in perturbation theory. So it remains a one loop contribution always, but the propagator that enters is indeed a addressed propagator, so that it is a way of sort of rearranging perturbation theory within a one loop diagram form.
So you say that this expression comes from a so-called functional renormalization group, yeah?
Yes.
Okay, thank you.
Okay, thank you very much. So now it's a question from Sasha Monin. Sasha, you're muted. Please turn on your microphone.
I'm really sorry. Yes, thank you so much. You answered already so many questions. I'm not going to take a lot of your time. However, I'd like to continue regarding the similar question that was asked just a couple of minutes ago. So I think I'm still confused with how this thing works. So correct me if I'm wrong. What you're trying to say that you want to have in the UV, you want to have scale invariance, right? So what it means that let's remove all possible reservations and remarks. In a sense, it should be that the energy momentum tensor should be traceless, because usually it's proportional to some beta functions. That's why you want beta functions to be 0, right? Mm-hmm. However, when the running is not logarithmic and it's power-like, I do not understand where is the universality, because what do you call the coupling? Right? When I talk about logarithmic coupling, then it's one and the same coupling that enters all the processes. However, if I talk about power-like running, I do not like it. S channel and T channel, different coupling is entering, right? So yes. How do you address this issue? Yeah. If at all, if this is an issue.
I mean, you're right. That it's a sort of a valid question to ask. I would say it's partially a question of sort of semantics, because people call running couplings different things. So there is indeed a community that refers to running couplings as just couplings that depend on the scale logarithmically. And then there is, as you said, a universality as to sort of that I can parameterize different processes in different channels in terms of the same coupling. Now, in this setting here, running coupling is understood in a somewhat broader sense. So here the running is understood as a function of this this RG scale that tells you how far you have integrated out quantum fluctuations. And then indeed couplings that aren't dimensionless will generically have a running that isn't a power law running. The way how this then enters various processes is that the appropriate way to think about it is not necessarily in terms of a single coupling that can parameterize different processes, but in terms of vertex functions, which depend on all of the momenta in the processes. And those vertex functions can then be used to parameterize the different processes, and then those vertex functions are actually the quantities that should become scale invariant at high energies. In a sort of then simplified approximation, one can then get back to talk about individual couplings. But depending on the process that one looks at, one really has to look at a full vertex function. But that is within this functional renormalization group setup. That is what people are actually taking into account. So looking at things like the 3 graviton or the 4 graviton vertex function, or at gravity meta vertex functions. So in the presentation, I sort of simplified things a little bit to reduce that back to sort of the couplings of the standard model. But depending on what scattering process you'd be interested in, you would really have to go back to this sort of slightly more complicated setting of momentum-dependent vertex functions.
Okay, so you're saying that you're taking momentum-dependent vertex function that depends on all possible incoming, let's put them all incoming momenta, and the cutoff, right? And then you're demanding that this vertex function does not depend on the cutoff. Is that the correct statement? That it does not depend on lambda?
So I'm demanding
or
that.
Not.
Yeah, I'm demanding that if I look at an appropriate dimensionless version of that vertex function, that actually becomes constant.
Yeah, sure. You first normalize to appropriate power of lambda, then you compute the derivative with respect to lambda, and you're saying this is 0.
Yes.
Okay. Isn't that too restrictive on the theory? So I'm thinking of just a simple process. Imagine that I do the leading order correction in k square over m Planck square, right? I compute one loop or whatever I need, maybe not even a loop, then the correction is going to be k square over or g times k square, or g times lambda square, where lambda is the cutoff.
Mm-hmm.
And now it seems to me that, so how am I supposed to make it independent of lambda? But moreover, for me, I don't think I agree with you that this is just a semantics. For me, it's not about the semantics. I don't care how you call what. For me, the question is, can you guarantee that provided that this function, whatever vertex function, is 0, that actually the symmetry is there? So can you show that there are conserved currents and conserved charges?
Mm-hmm. So I'm not completely sure whether there is a strict proof about the conserved charges or conserved currents. I would expect that story should go through, because this is just sort of the standard form of scale symmetry that is also imposed in any sort of statistical physics or condensed matter theory where I have fixed points or scale symmetry realized in the infrared. So in that sense, it's not exotic what I'm doing here. And indeed, the main idea about what happens to sort of scattering cross sections, that goes back to Weinberg's original proposal from the 70s, where you can show that if you take a scattering cross section and you write it in a dimensionless form, and then you isolate the sort of the coupling from the energy dependence, that if this dimensionless coupling or dimensionless part of the vertex function, whatever you want to call it, if that becomes constant, then you're really safe from UV divergences and you're realizing scale symmetry.
Yeah, but it seems to me that if it's not just one parameter, if usually what we do with RG, right, is just energy scale divided by lambda. Only one ratio enters. But now you're saying I have to take into account all momenta, like P1 square over lambda square, P2 square over lambda square. And for me, it seems almost inconceivable that this vertex function can be lambda independent. So if it's just one parameter, I can always say, yeah, I go to the cutoff, and then everything is given by the coupling at the cutoff. While otherwise, but look, I would like to learn more about this, but yeah, I don't think I should take more of your time. Thank you so much.
We can also discuss over email or similar. It also depends on the regime that you're looking at, right? So whenever you have this vertex function depending on various momenta, you need to make sure that you're looking at a combination where all of the momenta are appropriately at high scale, so that you're really looking at the regime where you're expecting scale symmetry to set in, right? And of course, depending on what combination of momenta you choose, you might not be looking at the really UV regime of the vertex function. But yeah, maybe this is indeed something to be discussed in more detail.
Thank you. Thank you so much.
Thank you very much for the questions. Okay, do we still have any other questions in the audience? Okay, then we had already a very big number of questions, so thank you very much again. Let's thank the speaker again for a brilliant talk. And thank you very much for all of you for participation. And okay, then have a nice day.
Goodbye. Thank you. Bye.
For the invitation.
Thank you very much.
Bye.
Thanks very much, Sasha.
Thank you.